So today we'll be starting with our the week two of these online meetings. Week three, sorry. And today we'll be starting with this linearization. So many times we have discussed about the linear and the non-linear systems. So linear system, we know that if the system satisfies the principle of superposition, meaning to say that the additivity and homogeneity properties are satisfied, then we say that the system is linear. And if the superposition principle is not satisfied or does not apply to a system, then we call it a non-linear system. So this we had seen that there is a input output linear relationship between the input and output, while for a non-linear system this is just an example that the input output relationship is not linear. So the first question rises that why do we want to linearize our system? So like I said, uh, that in this course we'll be studying mostly with the transfer functions and their analysis. So for a nonlinear system, you cannot obtain a Laplace transform or a transfer function. And so for a given nonlinear system, we will first linearize it to obtain a linear representation. Either it could be in the form of a transfer function or in the form of a state space representation to do our further analysis. So there are some physical nonlinearities, typical nonlinearities, which you would see possibly in your lab experiments as well. So first of all is the saturation. The saturation in the saturation, you see that the input-output relationship is linear within this limited zone. For this limited input, the output is linear with respect to input. But after this one, as you increase the input, the output stays constant. Similarly, here the output stays constant once you decrease this input. So these types of nonlinearities are called the saturation nonlinearities. That there is a linear behavior in this zone while it's a nonlinear behavior outside this zone. Okay, so for a given system, let's say we have this y of t and u of t, and let's call it the system S. So generally this type of saturation blocks you generally see as in front of the actuator. So we have this actuator, and the original input is, now let's call it u a of t, and this actuator would now behave as a saturation block, meaning to say, and this will be ua of t, and the output is u of t, which is going into the system. Meaning to say, if ua of t is in this zone, then u then there's a linear relationship between u and u. Afterwards, the u of t would remain constant irrespective of whatever you apply. Okay, so this is a most generic type of nonlinearity which you would see in your DC motor experiment as well. The second one is the dead zone. So on the x-axis we have the input, and on the y-axis we have the output. So the dead zone nonlinearity are such things that that the that there is a linear line between the input and output, but this input output line does not start with at zero. Okay, so there is this zone that if your input lies in this range, then there is no output. Okay, so that's why we call it a dead zone, and this is a common phenomenon in the DC motor, that once you start applying the voltage which is of minimal value, only after that you would see the angular rotation of the motor. Okay, the third one is the backlash in gears. So this backlash in gears is also a common phenomena which you can see in your daily life as well. If you are bicycling or if you are using gears for some pulling purposes. So the idea here is, see this figure, see this figure onto the right hand side, that there is some, let's say, one slab which is this one and another slab is this one. Okay, now if we have the, if there is no gap between these two things, then they are tightly coupled. So whatever the input you would give, there would be an output. Okay, depending on in which direction you are giving the input. But if there is some gap, this gap in the connection of this gear and this gear, then you would see this phenomena of backlash, which is basically like this. So there is a linear relationship between the input and output, but it does not passes to zero, and it is not coming through the same direction, because it comes in this direction. Okay, so this is also another type of nonlinearity. Now if we have such kind of nonlinearities, you cannot obtain the transfer functions and also the linear state space representation to compute its solution and do further analysis. So that's why we use this concept of linearization, where we want to obtain an approximate linear model for a given nonlinear system. So this is the idea. Let's say, so consider a nonlinear equation. So this equation can be represented as, in general, y is equal to f of u, where y is your output and u is your input, and this f is some nonlinear function. And this nonlinear function, for an example, you could see onto this graph, where we have on the x-axis as u and on the y-axis as y, which is a function of f of u, and this is some function f of u. Okay, so the first step behind linearization is we select an operating condition. Say, let's say, and this operating condition is generally named by several names. It could be the the equilibrium point or the steady state point. We will come on to this aspect. So let's say I select this operating point where I want to analyze my system. So this at operating point, let's say we have this u bar and I have this point as y bar. So generally, by linearization, we also mean that we want to do the small signal analysis, that around this operating point or in the vicinity of this operating point, how my system would behave. Okay, and there could be infinite number of operating points for a nonlinear system. But at the outside, generally you have some idea that around which operating point you need to analyze your system. We'll see, we'll take one example which will relate you through the linearization process. Okay, so let's select this u bar point and y bar point, and at this point I will draw a tangent. So I think you could see the zoomed version. So around this point I will draw a tangent, which is passing through this nonlinear curve. So what you would see here, that in the very close vicinity, this straight line actually overlap onto this nonlinear function, or there is a very little error or very less error. Okay, so let's mark this point, this one and this one, at the close neighborhood of u bar, and similarly add these two different points. We will mark the region of the output around this y bar, okay, which are our operating point. So now here the physical significance is, let's say, why do we, the physical significance of why do we only analyze this in a close vicinity of the operating point, because you see that whatever this tangent line we have drawn, onto this nonlinear curve, it matches very closely onto the nonlinear curve. Because if I, let's say if I uh, take a point onto this straight line here, then this point does not lie on the nonlinear function, because the nonlinear function is this one. Okay, let me use some different color. So nonlinear function is basically this one. Okay, and this point does not lie on this point. This point does not lie on this line or on this curve. Okay, so whatever the system or whatever the representation I would obtain around this point would have nothing to do with the nonlinear system. Okay, that's why we do the analysis only in the close neighborhood of this uh, operating point, right? Now let's mark this region as delta y, and similarly around this u bar we call it the delta u. Okay, so we make use of the Taylor series expansion what you have possibly studied in your plus 2 to achieve our objective. So starting with this y is equal to f of u. For this f of u function I will write a Taylor series around the operating point u bar. So if you recall, then the Taylor series written as f of u bar, the first derivative of function f with respect to u multiplied by u minus that operating point u bar. Similarly, you would have the higher order derivatives. But as we have seen in the physical significance of this from this linearization process, the higher order derivatives are of very less significant value. Okay, so we only go with the first order derivative, right? And all the derivatives, these df by du and d square f by d square, are computed at the operating point u is equal to u bar. Okay, now let's see if this variation, if the variation u minus u bar is small, which we have already ensured here, that around this u bar we only analyze in the close vicinity. So we know that u minus u bar is already very small, then the higher order derivatives can be neglected. So the remaining terms we have y from the left hand side of this equation, y bar, which is the operating value of that function around that u bar, we have labeled this y bar, and df by du at u is equal to u bar would again be some constant term. Okay, which we have labeled as some constant k, and we kept as u minus u bar, where y bar is equal to f of u bar and k is equal to df by du at u is equal to u bar. So the final expression we have obtained as y minus y bar is which is nothing but delta y is equal to k times delta u, and delta u is nothing but u minus u bar. So if you see this relationship is nothing but a linear relationship between the input and output, which are now labeled as delta y and delta u, and delta y and delta u are nothing but u minus u bar and y minus y bar, okay, around the operating point. Okay, so if we see what we have done, let's quickly recap that we have some function f of u. Okay, so this is our signal y and this is our signal u. Okay, now this is a nonlinear system, this is a nonlinear map. Okay, nonlinear function, right? Now by the idea of nonlinearization, what we want to see that we have this, let's uh, plug in this u bar, and similarly let's plug in this y bar. So y minus y bar is our delta y, and this is our delta u. So if we have this delta u as u minus u bar, then our u basically becomes delta u plus u bar. Okay, so this is a plus sign, right? So this is a nonlinear function which is inside this thing, and we want to analyze this u bar and y bar. Now if I see the map, this map from delta u to delta y, this is now a linear function around this operating point u bar and y bar. Okay, so this is what we have done by using the Taylor series expansion, and we want to be so this delta u and delta y are small signal around this operating point y bar and u bar. Okay, so this was the linearization process. So we can take one example just to apply this idea. But the main equation, let's write the main equation what we had seen. So we have this some function f of u minus f of u bar, which is our operating point, is equivalent or is approximately equal to the derivative of this function df over du computed at u is equal to u bar multiplied by u minus u bar. Okay, this is our main equation for the linearization. So let's take an example now. So we are so this is example 2.28 from the textbook by Norman Nees. Okay. So for example, we are given some a nonlinear electrical network which is given by this, where we have this V of t as a small signal. The current flowing inside the circuit is I of t. Let's take the inductor of 1 Henry, and the voltage across the inductor is uh, the voltage across the inductor is, let's call it VL of t. Okay, now this resistor, let's call it or denote it by R, and this is a non-linear resistor. By non-linear resistor I mean to say that the voltage across this resistor and the current flowing in this resistor are not related by a linear relationship. So there would be some non-linear relationship, and let's call it that the current flowing inside the resistor, let's denote it by I of IR, is equal to 2 e to the power 0.1 of voltage across the resistor. Okay, so this is the non-linear relationship between the voltage and current flowing generated or flowing across the resistor R, and there is DC voltage supply 20 volts. Okay, so if I write the simple KVL equation for this loop, I would have the voltage across the inductor plus voltage across the resistor minus the DC voltage of 20 volt is equal to V of t. Okay, so this VL we know is L di by dt. This VR we can obtain from here by taking the logarithmic of this. So it would be VR is equal to 10 ln 1 by 2 IR. Okay, let's substitute it here. So we would have 10 natural log 1 by 2 I minus 20 is equal to V of t. Okay, so this is the complete KVL equation. Okay, so now we will evaluate the equilibrium solution or the operating condition. So as we have said that v of t is already a small signal, let's take it equal to 0 and denoted by v bar. Okay, is equal to 0. Now we will obtain the steady state current around this v bar. So around this v bar, we know that the circuit consists of a 20-volt battery which is in series with the inductor and the nonlinear resistor. So in the steady state, the voltage across the inductor would be 0, since the derivative of the current is 0 at the steady state, and this is the VR. So we would have VR is equal to 20, and let's call it VR bar. Okay, so from this VR bar we can compute this IR bar, which is 14.78 amperes. Okay, you could use this formula, which is the nonlinear relationship of the, you put this V bar here and you would obtain this IR bar, which are the operating point, and this IR bar is nothing but the I, current flowing inside the resistance. So we will denote it this by I. Okay, oh sorry, this I bar, let's say. Okay, now we have obtained the equilibrium point, which is I bar, and the other signal is V bar. So I bar and V bar are our operating points. So now let's substitute what would happen in the closed neighborhood of this operating points. Coming back to this original equation, I would write L d by dt of some I naught plus, let's call it delta I. Okay, plus 10 ln by 2 I naught plus delta I minus 20 is equal to V of t. Okay, so now using this expression, we will linearize this nonlinear function, because this is a linear function, and only this is the only the nonlinear term here in this expression. So first of all we will focus on to this nonlinear term by using this formula, and then we will see how we can obtain the transfer function. So using that equation, I can write ln 1 by 2 minus, so this is fx plus x naught, ln half of, maybe I have used different notations. So this I bar, so just a minute. So this is basically your I bar. Okay, we'll use the same notation. So this is I bar. Okay, minus ln half of I bar is equal to the derivative of that function, which is ln half I at I is equal to I bar and then delta I. Okay, and this would become equal to your 1 upon I at I is equal to I bar and delta I, which is nothing but your 1 upon I bar delta I. Okay, so the expression I would have is ln 1 by 2 I bar plus delta I is equal to ln I bar by 2 plus 1 by I bar of, excuse me, delta I. Okay, and now this is a linear expression. So I will substitute this one here into this part, and finally I would obtain this L d delta I by dt. Okay, now this complete expression is a linear equation. So after substituting your L is equal to 1 and this I bar which we have obtained above is 14.78, we will obtain the final linearized equation as d delta I by delta t plus 0.677 delta I is equal to v of t. Okay, now assuming the zero initial condition, you can also this is the first order differential equation. So assuming the zero initial conditions, you can take the Laplace transform to finally write the transfer function, which is delta of is by v of s is equal to 1 upon s plus 0.677. Okay, so this is the transfer function as the ratio of delta I over v of s. Okay, so this is how you can linearize the system. So if you have any doubt about this linearization, then we can take now, or any other doubts in the tutorial problems. So I think we can stop here on this so I think we can stop here on linearization today, because from the next class we will see the time domain analysis, or basically the responses and some performance indices or specifications. So if you don't have any queries in this linearization procedure and its physical significance, then I think we can